Well, welcome to the Friday lecture. You are the sturdy ones that come even on a Friday. That's very good. Any questions to start? Oh, yeah, go ahead. And if there's any questions. I just wanted to say that of the material we're covering now, I'm not holding you responsible for a lot of the details, and I'll send you some email about what sections we won't be responsible for. Like there's a lot of details of counting the number of states in a level and things like that. I think maybe something on the homework that just to get you a little into it, but I won't hold you to it for the exam. It's a little bit too detailed, and there's a bunch of material on the analyzing the periodic chart and chemical elements. That's a bit too much also. I think you can learn a lot of that material in chemistry if you need it. So I'll give you a list of things that we won't be responsible for on the tests in particular. Now, as usual, I'm running a little behind what I'd like to do. I wanted to get into solids by today, and I don't think I'm going to make it. So I think we'll just work through Schrodinger's equation as applied to hydrogen and other materials, atoms, gases. Now solids we should do because it's very interesting, but next week you have a lab on radioactivity. So I will do, on Monday, I'll talk about radioactivity just to get you warmed up for that, basic ideas. Then I'll go back to solids on Wednesday. Doesn't really matter which order we take them in, except that solids would follow a little more naturally from this material, from atoms, because the quantum mechanics flows directly into solids. But unfortunately, I didn't get there. So we'll do, I think, radioactivity on Monday. We'll do solids on Wednesday and go back to nuclear on Friday. We end with a bang for the course on a week from today. So that's going to be the schedule. I'll post that also with some more PowerPoints on. I think I just put solids up already, but I didn't put up nuclear yet. And again, we won't do everything in nuclear, and we won't do everything in solids either. Obviously, in a couple of lectures, there isn't much you can do beyond the basics. But I did want to go over how wave mechanics explains a lot of things that we find in nature, in atoms, and it's one of the triumphs of physics that we have got this far. So I've drawn up here the energy scale for the hydrogen atom that you've seen before, and that is that if you take an electron and you bring it close to a proton to make a hydrogen atom, you start out with the energy 0 at a large distance. You bring it in, and the electron will fall into the potential of the hydrogen atom with the usual Coulomb potential energy that we've seen before. Now, because the plus and the minus charge have different signs, E times E will give you a minus sign here. And so when you see a negative total a potential, it means that it's trying to bind the system. The point being that it will take that much energy, if that's the potential energy, it will take that much energy to get you back to 0. So what happens is the particle comes in with 0 energy and it loses energy. It must get rid of some of that energy in order to have less than the energy it started with, actually. So it actually must have radiated some energy out in order to become trapped in the hydrogen atom. And what that means on the other side is that to get out of the atom, you have to put energy in. giving it back the energy it's sort of dissipated and coming into the well. So that's the picture of what's going on in the hydrogen atom. Now, Bohr used this picture using this potential energy and ordinary kinetic energy, and he solved for the energies with the assumption, as we've said, that the angular momentum, mv, r times mv, is this quantum, h bar. And what he came up with was this model, and let me show just on the space here the Bohr results. Starting with, he found that there was a lowest energy here at minus 13.6, and what the picture he had was the electron going around in a circle. He assumed circular orbits, again the simplest possible case, and that this, with the assumptions that we have discussed before, the energy that I wrote and the angular momentum being quantized, you come up that there is a minimum radius of this orbit, which turns out to be 5 times 10 to the minus 11th meters. And that the speed at which this thing is going around is, actually, I had the number here, I think I calculated just a little while ago. It's quite fast. It's going around at 2 million meters per second. If you actually calculate what the speed of that particle would be, in order to keep it in that orbit, you see, because you want it to go fast enough so that it doesn't get pulled into the plus charge, not so fast that it leaves the atom altogether. And it turns out at that speed and at that radius, you have the correct, 2 times 10 to the 6th. That's a 6th here. Sorry, that looks poorly written. 2 times 10 to the 6th. So it's 2 million meters per second the electron is whipping around there. Now, one thing I should point out, that the Bohr theory can be extended to more than just one positive charge at the center. For example, if you have a heavier element, its charge will not be E, but we recognize the elements by ZE, right? The Z is the letter given to the number of charges. We call it Z. So, for example, helium Z equals 2, lithium Z equals 3, et cetera, et cetera. You know the chemistry. Okay, so when you put that, you see, into the force formula, you have ZE times the electron charge. This is the nuclear charge. This is the electronic charge. You follow through the theory, and you find that the energies in the Bohr theory, the energies of the nth state go as the Z squared times the energy of the ground state, which is, we call it E0. So it goes as a square because the energy of the ground, this state here, the lowest state, goes as e to the 4th. Well, the e to the 4th is it's actually the charge of the nucleus squared times the charge of the electron squared. So if the charge of the nucleus is going as ZE, you get this squared, and this is E squared. So you get Z squared e to the 4th. That's where the Z squared comes in, and the formula will have the e to the 4th in it. If you look back in the energy formula for the hydrogen atom, it will go as e to the 4th. Half of that is going from the nucleus and half from the electron, so you get a Z squared. That'll turn out to be interesting later in this talk. So the formulas that you have for the hydrogen atom, they should have, wherever you see the nuclear charge, you could make it apply to heavier elements by simply multiplying the nuclear charge by Z, and however it follows through the formulas, you'll get an answer. So in any case, yeah, and the other things that go on are that the velocity of the nth state is the velocity of the ground state, which let's call it, because everybody seems to call that ground state 0, for some reason I would have called it 1 myself because it has one angular momentum, but that goes as the quantum number n, so that actually what's happening, and also what's happening is that as the n state goes up, the particle is actually going slower. When it goes into larger orbits, it goes slower. And the radius that it goes on actually goes up as n squared. So it's n squared times the radius of the lowest state. So if you were to draw the Bohr pictures, you start out with the ground state, which somehow they're calling 0. A0 is usually the way they write the first Bohr orbit. The second Bohr orbit is not at is up here at, we figured out as minus 3.4 or something like this, right, up in here. So its radius has gone up by the square, so its radius is now, the radius of the second orbit is 4 times the radius of the ground state, and its velocity of the second state is 1/2 of the velocity of the ground state. So the picture you have is that in the ground state, the electron has this Bohr orbit, the first Bohr orbit, as they call it, 5 times 10 to the minus. As you go up, your radius goes up 4-fold, so it's now 20 times 10 to the minus 11th meters. It's going in a bigger circle, but it's going slower. And it will also have the angular momentum will be 2h bar over here. So that's the way it is. And if you go to the next higher level, which is the 3 level, level 3 is at 1.5 volts down, minus 1.5 is about here. And again, you can do the same kinds of story. The orbit will be, because this is the 3rd level, it'll be 9 times as large as the first Bohr orbit, and its velocity will be 1/3 as great. So you're getting a big, fat orbit, and the orbits get fatter and fatter. I think in the book, he says, what happens at orbit number 200 or something? The orbit number 200 will go as a square, so it goes 200 squares, gets to be really big, and in fact, these are sometimes, well, it suggests that the orbits could be enormous, but something will happen, I'm sure. If the orbit gets to be about 1 centimeter, I think somebody's going to bump into it, you know. I mean, it doesn't seem plausible that you could have a hydrogen atom with an orbit 1 centimeter big and nothing strange will happen to it, like run into another atom, you know. So anyhow, but theoretically, the orbits go as the square of the quantum number, and that can get pretty large. Okay, so that's basically the Bohr way of looking at things. And it's relatively straightforward. You just have larger circular orbits. And that's about as far as Bohr theory could carry you. Then along came Schrödinger. And, well, before even Schrödinger came de Broglie. And de Broglie, even in his thesis, recognized that by introducing the idea of waves, he could go a step beyond Bohr. Did you have a question? Okay. He had the point was that when de Broglie said that the momentum is associated with a wavelength, that or if you will, lambda is h over the momentum, p being mv. de Broglie's idea that he said right up front was that if there's a wave going around a circle, if it interferes with itself coherently, then you might have something special happen. You have kind of like a standing wave. And so let's imagine you start out with an electron here, and it's going around the orbit, and it goes, below the line first, and it comes back on itself, and this is one wave, and so that to have a super constructive interference, you would have to have one wavelength, say, in the distance you go around the circle, which would be 2 pi r. And he says, well, let's see what happens if you do that. Let's say you have a standing wave where the wavelength just comes back on itself nicely. So you then put lambda as h, and his theory says lambda is h over p is equal to 2 pi r, in which case you get immediately h equals 2 pi r times p, just multiplying across, and you just divide by 2 pi, you get h over 2 pi is equal to r times p. And that's what Bohr said, that Bohr assumed, that the this angular momentum here, or down here, is in the first state, it's h bar, which is h over 2 pi, which is r times p. So whereas Bohr just stuck it in and said, look, it works, de Broglie went one step further and said, well, the reason it works is because you have a wave, and the wave is constructively interfering with itself, and it gives you exactly the angular momentum quantized in units h over 2 pi. So that's a dramatic step forward, because instead of just picking it out of the air, you have something backing it. And of course, the idea that the thing, a material particle has a wave associated with it, was confirmed by doing wave-like experiments on it, like interference, scattering it off of materials, like we did in the class here. We shot electrons through graphite, and we got interference patterns. That, as far as we know, only waves can do that. So this is a little harder to confirm, because you can't look at an atom and just see what it's doing around the loop here. But it certainly was provocative that it could be extended even to trying to explain atoms. And then Schrödinger, who was, I think, at that time he was actually in Switzerland. He was at the University in Zurich. And somebody apparently in a colloquium who was talking about de Broglie's ideas said, look, if it's a wave, there should be a wave equation. So Schrödinger put his head to it and came up with his wave equation. And let's see what that wave equation says about the atom. Now, the difficulty for us is that we so far have talked about one-dimensional problems. We've had a wave which is more or less just in the x direction, and we can handle that reasonably well. Now, the hydrogen atom, on the other hand, is a three-dimensional problem. Basically spherically symmetrical. The electron is going around all 3 dimensions. So XYZ is not exactly the best way to look at this. I remember from your calculus courses that you have another set of coordinates that are more suitable in the spherical geometry, where you can have a radius vector. So that's one coordinate. And then you can have the angle between that radius vector and, say, the z-axis, which is typically called theta. And then you have yet another angle in here between the projection of the radius vector on this plane and that thing here. That's your angle phi. You remember those bad old days. when that was thrown at you. And you have to work in that funny coordinate systems. Well, Schrödinger said, well, that's the way a spherical atom will look. So I have to work in those conditions. And so instead of having what we had before, which was an equation that had derivatives with respect to x, y, and z, or at least x squared is all we've ever done, you then have to have an equation in terms of these more appropriate variables, r, theta, and phi. And that's a little more complicated equation. Schrödinger was able to deal with it. And it breaks up, actually, into three parts. You have the total wave function that he gets has a radial part. It has a theta part, goes this way, which is a function of theta, and a phi part, which is related to the angle phi. So it turns out that you can, the equation breaks up into these three parts, and you can solve each of those equations separately. And the interesting thing is that every one of those parts becomes quantized. That is that you have to solve an equation where, for example, the radial part would be something like this. You ask for the radial part as a function of r. It has to do the right things. That is, it has to vary, and then it has to get small. Remember all those things we talked about in the one dimension? It has to do all the same things. Namely, you'll get not one that doesn't, a solution that doesn't wiggle much, but dies out as you go to infinity. Then you get a solution that wiggles a little more, one more wiggle, one more crossing, you might say, where the function crosses. This one has 0 crossings, this has 1. And then you have yet another solution which might have 2 crossings, maybe something like this, and then goes to infinity later, like that. So, but they're all quantized. You see, you'll have distinct solutions. Again, the same issue that I try to illustrate for you in the box here, namely that if you start out with a solution, the wave function must fit into the potential and die out at large distances, or else you can't normalize it. So there are only specific solutions that work, and you get specific energies corresponding to these solutions. The same is actually true in the theta direction. There are just certain shapes that will fit in that direction. So even that direction is quantized. And also, as you go around in circles, you get quantization going around in that direction. So you get this series of quantum numbers. Yes, sir?
What is the H, Professor?
The what?
The H that circles it, just a hydrogen atom? What is the...
I'm sorry.
You say R of R, H.
Oh, that is supposed to be capital theta. That's supposed to be capital theta. It's a function of the angle theta only. It's a function. It's the function capital theta. Yeah, I don't know how. I think that's the way it's written. Okay. Yes, that's supposed to be capital theta. It's a function of theta. It might look like something like this: cosine squared theta minus 1. That's the kind. That might be one of the functions. In fact, it is one. It's actually 3 cosine squared theta. This might give you kind of a shape like that. Yeah, and then phi's, functions of phi tend to look like e to the I phi. That's a phi of little phi, function of phi. So it turns out that the functions of phi tend to look like this, and the functions of theta tend to look like this, and the functions of r tend to look like r e to the minus r over some radius of the atom. So, for example, the r of the ground state, you might call it r0, is this has various powers of r. So the first one actually is e to the minus r over a0. Sorry you asked. No. Okay. So no. It's better that you see roughly what they look like. Yeah. The R functions are just functions of R, and they tend to have an exponential in them and some power of the R in front of it. And that's actually going to come up in a second. And the functions of theta tend to be something which, as you vary theta, they will vary, like 3 cosine squared theta minus 1. And phi, it tends to look like e to the I phi. So that varies, sort of like cosine-like as you go around in the phi direction. I'm not going to knock you out too much with that, but just to see, having seen it. That's what Schrödinger did, and a lot of this stuff apparently was already done by mathematicians. So Schrödinger was very happy. Apparently, a book had just come out, a book by Courant and Hilbert, 2 mathematicians, in 1924, wrote a book on mathematics for physics. And Schrödinger discovered that book and just gobbled it up and just came up with all these things. And in fact, all of these things tend to be, the French, I think, again, I keep coming up, they seem to have solved all these equations as part of their just mathematical thing. So they all have French names, like these R functions that look like this are called Laguerre functions. These are called Legendre polynomials. This one is too simple. Nobody takes credit for that, even the French. That's too simple. But the complicated ones apparently were all solved by the French mathematicians who were very strong in the 19th century. So this is pretty old stuff for a mathematician. But for the physicists, this was great. Okay, so what were the answers here? So what Schrödinger came up with was, let me show you here. First, let's just sort of draw the wave functions the radial wave functions. For the first state, as we said, it's a simple exponential dying out like that. So this is R, the R function, as a function of R. And this, I'm going to put it here at 13.6 eV, so you'll see what belongs to what, as it were. And that's a function of R, and that's that function e to the minus R over A0, where A0 is this number 5 times 10 to the minus 10 to the minus 11th meters. Okay. Now, in our book, I don't know that this is actually pictured so much. What the book talks about is not so much the radial function or R of R that I'm calling it, or even psi of R. That's a little bit of a misnomer because psi is really the product of all these different parts. But if you try to find where the particle is, the formula is to square this function. That's the probability per unit length or per unit volume. So to get the actual probability of finding the particle at R, anywhere at the radius R, you should multiply by the volume element. In other words, I'm trying to find can I find a particle within this shell at radius R from the center? Where is the electron? Is it in that shell? I have to multiply that by the volume of this shell, which is 4 pi r squared, which is the surface of the shell, times its thickness, which is dr. So that's an infinitesimally thin shell. So I should multiply this by 4 pi r squared dr. So that's the probability that you'll find an electron within this shell of thickness dr at r. So this is the probability that's written in your book. And so you would, if you plotted P of R, when you multiply by 4 pi r squared, well, r squared is 0 at r equals 0. So that, let me show you perhaps. You see in your book, they plot P of R. And I explain here that the wave function psi is going exponentially down. The volume element, 4 pi r squared dr, is going up like this. But at 0, when you multiply the volume element times psi squared, you get that the probability is 0 right at the center. But interestingly, it isn't a 0 a little bit of a distance here, so that in fact that first state has some density inside the nucleus, according to this theory. Whereas very different from Bohr's theory. Bohr's theory said the electron is way out here, running around in an orbit, well, doesn't touch the nucleus. Schrodinger's theory says, even though I'm killing it off by a 4 pi r squared thing, there is some probability, if the nucleus has any dimensions at all, right in here, ever so close, you will get some electrons sort of sitting inside the nucleus. And that actually has been observed. Because what you can get is that since the electron is right there, it sometimes is captured by the nucleus. And a proton captures an electron, turns into a neutron. So that is an experimentally observed phenomenon. Another phenomenon that is observed is if you do nuclear magnetic resonance, it turns out that the electron has some magnetic spin and magnetic properties. So there is a magnetism right at the nucleus due to the close-in electrons, and that's an observable phenomenon too. So it's interesting that the theory says that the electron should be sitting right on the nucleus, and it is observed. So that's your understanding of the wave function and the probability of finding the particle, because the probability is this product of the square of that times 4 pi r squared dr. Did you see that? That may be a little confusing in the book. Maybe not, I don't know. So in the pictures in the book, you see the fuzzy dotted thing up there. That is actually plotting this function, the R function, because it's intense at the center and dies out as you go down, whereas so that's psi of R. See, it's intense at the center and it gets weaker. So that's sort of the probability. That's psi R squared. That's R squared. And here is the probability is R squared multiplied by that volume factor. Okay. So, now Schrodinger then says this equation has other solutions that fit the fancy equation with all the R's and the thetas and all that. The second one, but the other thing you want to notice is that it turns out that the energy of that state, in Schrodinger's theory, that state, what Bohr found at minus 13.6, is exactly the energy that Schrodinger finds. So he gets the same energy. So that's the same. And he gets also that the peak of where you might find the electron comes out also where Bohr said is the Bohr radius. Yes, sir?
How was he able to exactly find that?
You just go into that equation, you grind away, and you find the energy, the energy of that state. Again, that state has to fit into all these conditions. It has to start someplace, die out, fit in. It can't do anything crazy. It can't go like that. It can't go like that. So there are very few energies in his theory. Again, you have kinetic energy, potential energy, and the total energy. You can vary the total energy like I did, and you can see the wave functions going crazy, crazy, crazy. And you keep varying that energy until the wave functions do the right thing. At that energy, that's a real energy of the system. Comes out 13.6. Fabulous. Which not only agrees with Bohr, it agrees with the reality. It's even better. So he actually finds that that's the energy where you get a function which does all the right things. Normalizable, curves nicely, all that. Then he says, well, there's not only that solution, but there are other wavy solutions, which again, if I vary the energy, those solutions will do the right thing. And where did the energy come out? Minus 3.4. Right at minus 3.4, you get another wave solution. Now you're going to guess what that one looks like. If that one looks like this, the next one has to be, by our thinking, it has to be a little more wavy. And sure enough, starts out here, comes down, it's a little more wavy, it cuts the axis once, and he gets this kind of solution. And when you get this kind of correct solution, where it starts out and it goes to infinity, goes to zero at infinity, and it fits in the potential, just exactly at minus 3.4, and it looks like that. So it's just a little higher kinetic energy, meaning it's more wiggly, suggests more kinetic energy, and it comes out again exactly at the Bohr energy. So the Schrödinger energy is again minus 3.4 eV. It's going as you're doing in your homework over 1 squared, and this is the minus 13.6 over 2 squared. So it's the n value squared. Exactly the same. So far you say, okay, so what's all the fuss? Why not stick with Bohr? Well, but there's yet another solution here. And this goes back to our idea of the Chladni modes. If you go higher in energy, you're going higher in frequency. So you get a new kind of pattern can develop at this higher frequency. And what does that one look like? Well, this turns out that this, in a sense, the potential energy here is a simple minus E squared over 4 pi epsilon naught. Turns out that there is another set of solutions at this level where actually the potential is somewhat different, because the particle, instead of being in an orbit that's coming close to the nucleus, it turns out that there are orbits that circulate further from the nucleus, which it's again one of these Chladni modes. In other words, here you'd have a mode, if you were a Chladni plate, where you have stuff, piling up over here because it's a node and jiggling around over here. Now you can get yet another mode at this higher frequency, which now looks, again, the simplest kind of mode, like that. So that's your R for the second level. This is an R for the second level, but it's of one type. Let me call it 0. And here's a mode for the second type. I'll call it R2 and 1. See, what I haven't... So you see, we're starting a whole new set. And this, because it's the lowest mode in this new set, it's simple. It's just got one bump. So this should feel about right in that the simplest modes don't wiggle much. The next one does. Okay, now, just to complete that thought, if you go yet higher in energy, higher in frequency, you get yet another Chladni mode. At the third level, where was that? That was at minus 1.5, I think, right? Wasn't it? Down here, minus 1.5. So if you go there, let me put it in a different color just so it'll stand out, perhaps. Again, I want you to guess, what does that next mode look like? More wiggles. It's a higher mode in the same potential. So you get more wiggles. Instead of just going down and coming back up, it comes up over and does this. So this is the radial mode at the third level. So it's higher energy, higher frequency of the 0 type. I'll explain what that second number means. And correspondingly, you get another mode of this type but the next higher development of it in the third level, so what will it do? It'll be more wiggles. You get something like that. So this will be the radial function at the third level of the type 1. And I'll explain more what type 1 was. But because you're at a higher frequency, you can get a whole new set starting with yet a different potential, turns out. This is the potential of type 2. This is a U of a type, well, I'm calling 1. I'm sort of designating this. And so it starts out at 1.5 volts in here. And because it's the first of its type, it's the lowest mode. So it looks simple. So I don't know if you're picking up the pattern here, but in any one potential, you start out with the simple mode. The next higher mode in that same potential must be a little more wiggly. The next higher mode, it's the Chladni mode, getting more and more complicated as you go up. Then if you have a different potential, you start out with the lowest mode, simple. The next one has a little more wiggle, and so on. And then if you go yet higher, you start a whole new series, which looks like that, and on and on and on. I hope this is not too much. But the point is that we have names for all this. The thing that's different, what this number here means, if you actually calculate the angular momentum of the electron in these states, it turns out that the angular momentum is 0. Where shall I put that? The angular momentum is 0 in these states. What does that mean? You'll notice that the wave function is actually finite at the origin, the radial wave function. What that is saying, here is my picture of the radial wave functions. It says that the electron has some wave function at the origin. Granted, the probability is small because the volume here at the origin is very small, but the electron is trying to come to the nucleus. So if you look at the picture, how do you get that the angular momentum is 0? Well, the angular momentum is r times p, or r times mv. The mass is never 0. This is an electron we're speaking of. The velocity can't be 0 because otherwise the thing would crash into the nucleus, which would be sucked in. So the only way that the angular momentum can be 0 if r is 0. So what do you get? The crazy picture of the electron must be zipping straight through the nucleus, such that its velocity and its r are zero. There's no it's a cross product. So what you have to have something going sideways in order to get angular momentum, right? It's going around. So the picture is in this lowest state here, where the electron has a probability of being sort of in the nucleus, that it must be going straight through the nucleus back and forth like this, having 0 angular momentum. So these are states with 0 angular momentum, or sometimes written L equals 0. The difference here is that you see here the electron peaks up. It doesn't have any value at the radial function doesn't have any value at the nucleus. So this is an orbit indeed going around the nucleus, and the angular momentum here, L, is not equal to 0. So that's what this number here is. This is the L equals 1 state. It's getting a little bit hairy, I'm sure, for you, but the point is that in this state, the electron has finite, very strong probability of going around in a kind of circular orbit, and it has angular momentum. And in this state here, it turns out that this peak is even further out, so that the angular momentum, again, is not equal to 0. In fact, it has The number, it's a little bit strange, but it's the total angular momentum is this number L times L plus 1 times h bar. So in any case, the point is that as you go up in quantum numbers, you get, and here's where Schrödinger's picture really blossomed. Instead of the simple Bohr picture of having one level and another level here and another level here, simple thing like that, you get this rich picture of many, many states possible. And some of them have zero angular momentum, some of them have 1 unit of angular momentum, and some of them have 2, and it goes on and on. This we call the S states. These are called P states. These are called D states. And so you've seen that in your chemistry, I think, and also in the book. The other thing that's different about this is that not only do these orbits, this one have an orbit, but the other thing is that the orbit can take a certain tilt. So that you can have the orbit, for example, going like this, with an angular momentum upward, another particle's going around this way, and we would say that the angular momentum, the m value, this is the magnetic quantum, because it makes a difference. See, if this is a magnet, if there's a magnetic field here, if this is a current, see, there's an electron going around, so it's a current, it has a magnetic moment. If the magnetic moment is here, you have one energy value. If the magnetic moment is here, you have a different energy value. If the magnetic moment is here. So depending on whether the electron is going that way, let's say, I'll try to make it graphic, or if it's coming the other way, and so the magnetic moment is downward, it'll have different energies in a magnetic field. So a magnetic field, depending on the tilt of the orbit, see, you'll have a magnetic moment if you have a magnetic field, depending on the tilt. And it'll turn out that even this, because it all satisfies equations like that, they have different energies in a magnetic field. So these are your so-called M values, or M sub L, projections on an axis. Now, again, I think maybe I've again overdone this, but I wanted to have you see the power of this method. You get all these energy levels, and this is the hydrogen. Now, the other elements have roughly this kind of structure. The difference is that you then have many electrons, and you put them into these states, like this one. Again, we have this other quality that you have. Turns out, spin. The electron is spinning about its own axis. So not only do you have the electron moving in an orbit, which gives one kind of magnetism, if you will, but it's also spinning on its own axis. And so you have a magnetic moment of each electron. Once you get this kind of a setup, and you put electrons in all these orbits, as you've probably seen, you have to put every electron must have a different total quantum number. So you have to have the n quantum number, the L quantum number, the m quantum number, and the spin quantum number all have to be different. This is what's called the Pauli principle. And you fill up the states, and you fill up the levels, the lowest energy first, and you fill up states like this. Now, I wanted to demonstrate for you X-rays, because you will in your life either use them or be used by them or abused by them. You will be X-rayed at some point in your life for sure. And I wanted you to see what it looks like. What you're doing with an X-ray is you're taking one of these atoms that's got all kinds of levels in it and electrons. So you take, I think I have in my PowerPoint molybdenum, which is, I think, element something like 52. And it's got 52 electrons in it, all of them in these various states, in here. And what we're going to do here is we're going to shine in electrons at a high energy with a very high voltage, and we're going to knock an electron out of one of these states by hitting it so the electron is going to come in, an electron is going to pop out, electrons in with enough energy to eject an electron from this material. And then what's going to happen, because there's an empty space here, one of these other electrons is going to drop down into that space and emit in that process a frequency proportional to the amount that it drops. If it drops, it's going to drop into a state like that. And because of the z squared factor in the energy levels here, these energies are quite strong, quite large. They're in the range of tens of thousands of volts. Energy differences between here and here. You just take 13.6 and multiply it by 52 squared. That's 2,500 times 10 is 25,000 volt difference between this level and that. Well, that's between here and here, and most of it is actually in the first level, right? Because the first levels are separated in hydrogen by 10 out of 13. So even take that 10 here, that difference 10, multiply it by 250, get 25,000 volts. So you need at least 25,000 volts in to get the electron out, and then you're going to get a 25,000 volt photon coming out. That's your X-ray. That's why they're dangerous. I mean, this box here is covered with lead and so on. And what we have here, you can come by and see it later. There's a tiny little toy bear with a wire frame, sort of a wire hanger frame here, and there's an X-ray tube which looks something like this. The electrons are coming across, they're being attracted to this side, and there's a target over here. Better, let me draw it this way. So the electrons, as they're trying to get here, they hit the target, and out of the target comes the X-rays, and here's the little bear with his wire frame, and you'll see the shadow of his frame, I suspect. So I'm going to turn the lights out first. I hope. No. Nothing works. Okay, let's try these guys. Now I'll turn this on. And, well, this is nothing too surprising to you if you've ever seen an X-ray picture, which I'm sure you have. It's kind of spark. Do you see the shadow of the frame? There's a fluorescent screen. The X-rays are coming from a tube, kind of flickering in there. And passing through the frame, the wires are dense and they block the X-rays. So you're getting a shadow of the frame. And can you see it way back yonder? More or less? Okay. It's kind of an old setup, but what you can do if you like, come by and take a look, because I don't know if you'll ever elsewhere actually be able to look inside an X-ray machine to see what it looks like. But this is basically what they are. I turn that off to keep us healthier. So I think that's all for today. If you want, come by and just take a look at the setup that you've seen. Or maybe at this point I could even turn the